Hi guys, welcome to section 4.2 where we're going to continue on hypothesis testing. Now in today's lesson we are going to be looking at measuring evidence against the null hypothesis using the p-value. Just to summarize though, from where we left off with 4.1, we focused on the hypotheses and kind of what a hypothesis test is all about in statistics. So here's the summary from my notes from 4.1. Statistical tests use data from a sample to assess a claim about a population. Statistical tests are usually formalized with competing hypotheses. So there's a null and alternative hypothesis. The alternative is the research hypothesis. And a randomization test, a hypothesis test, examines whether sample data provide, and we said provide enough evidence to refute the null hypothesis and support the alternative. So enough is sort of a quantitative word, so we're going to have to think about how we're going to quantify what we mean by evidence against a null hypothesis. And that's really the aim for today. Now today in this lesson I'm doing something much different than I usually do, because I know we've gotten to some difficulties working with R and getting the coding down. I've decided to go in a different direction for these first few sections, and I'll probably have a separate screencast just giving an overview of this. I'm going to be working pretty close to the text and using their notes for some of this, something that I don't usually do, but I think it's quite a focused lesson on this measuring evidence with p-values. Separately, I'll do some examples and a little activity to reinforce some of the ideas. And we'll be using the StatKey software or StatKey applets that come with the textbook for some of these first sections in Chapter 4. And just at the end, then, we'll go back to R and see how we would carry out these procedures in R for a variety of situations. Alright, so let's get started then. Measuring evidence with p-values. Let's take a look at a study first. And this study asks a question, does drinking tea boost your immune system? So there was an experiment carried out to look at this question, and we're going to use this as a motivation for the idea of measuring evidence using the p-value, or at least using measuring evidence in a hypothesis test. Here's the reference for the study. And in this particular experiment, participants were indeed randomly assigned to two groups. First is to drink 5 or 6 cups of either tea or coffee every day for 2 weeks. Alright, so either tea or coffee. Both drinks have caffeine, but only tea has L-theanine. So after 2 weeks, blood samples were exposed to an antigen, and production of interferon gamma, the immune system response, was measured. So we want to see whether there was a difference between the two groups. Our explanatory variable is whether they got tea or coffee. And the response variable was the immune system response, measuring the interferon gamma production. And so the question is, does drinking tea actually boost your immunity? So we're kind of controlling for caffeine with comparing this against coffee. We want to see if there's evidence that it actually boosts your immunity. So here are the hypotheses we would set up with the explanatory variable and response variable as we define them. The question was about whether tea boosts immunity. So we could define two parameters, and remember at the outset of your test, always define the parameters so it's clear what you're talking about. So mu t is the mean immune system response after drinking tea. Mu sub c is the immune system response after drinking coffee. Alright, so coffee and tea. And let's see, so I just wanted to highlight those are the two groups we've got, right? Tea and coffee. Alright, so our hypotheses are that the means are equal, and the alternative is that the mean interferon gamma for the tea, those who drank tea, should be higher than for those who drank coffee. So let's have a look. Here's the data that was collected. So we can see in this diagram, these box plots comparing the coffee group with the tea group, that the median response, the middle of the line, is higher for tea than coffee, and the overall box seems a little bit more spread out. But the question is this a real difference, or could this just be explained by chance variability? The difference in the average response was 17.12 in the interferon gamma production. So there are two possible explanations. Why might the tea drinkers have higher levels of immune system response? Well, the first explanation is the alternative or research hypothesis was true, that tea drinkers do indeed have higher immune system responses than coffee drinkers. The other explanation, the other plausible explanation, is that the null is actually true, and all that we're seeing in this difference of 17.12 is random chance, that the people who got randomly assigned to the T group just happen to have better immune systems, or somehow just random factors resulted in them having a higher average, just due to sampling variability. So we want to try to identify, or see if we can determine, which is more likely in this situation. The null is true and this is just chance, or that indeed the alternative is actually true. So we're looking to try to assess the plausibility of the null hypothesis. So the goal in a hypothesis test is determine whether the null and whether the null hypothesis along with random chance are a plausible explanation given the observed data. Alright, so we want to think about what kinds of statistics might we get just by random chance if the null hypothesis were true. So to help us look at that, we're going to first look at how the actual experiment was done, and then we're going to see how we can use simulation, computing, to try to understand how unlikely or likely those results would be if the null hypothesis were true. So let's take a look. We had individuals recruited to participate in the study and who agreed. The design was to randomly assign units to treatment groups. So we can see that randomization was taking place just due to chance. And people got assigned to either the tea or the coffee group randomly. So here's our setup. We've got some in the treatment and some in the control. And so that's how the experiment was actually carried out. We randomly assigned units, randomized to treatment groups, conducted the experiment, measured the response, and here's the data that we got. So the tea group and the coffee group. All right, so we wanted to calculate the test statistic to summarize this, and that's a 17.12 that we saw before. These average to something that's to a value that's 17.12 units higher than the coffee group. So we haven't proven anything. We don't even know if we have evidence for anything. So that's what we want to consider here. Thinking about the actual results, there are two plausible explanations. Either T boosts immunity, and these are in fact higher, and they're reflecting that, or that this difference is due to random chance. So how do we assess whether random chance could have explained this? Well, what we're going to do is think about this data as our observed data, and then we're going to see, well, just due to randomization, what could have happened under the null hypothesis? That is, if there was no effect, and this was just due to chance that we got this split, how likely would a difference of 17.12 be? All right, so let's think about how we would do a simulation. So we're going to take these observed values and pull them together. So we've got a pile of response values, and now we're going to kind of repeat the randomization of the experiment many times. So we take these values and we're going to randomly assign or re-randomize to treatment groups. All right, so just due to chance, we're randomly assigning certain values to one group or the other, and we continue that, and so we get the observed data. Sorry, not the observed data, but this is the first re-randomization. We could take these values and then calculate the difference just for this particular value, calculate it. And in this case, just due to chance, we pulled them together, then did a re-randomization. Now in this case, turned out that the tea value was 12.3 units lower than the coffee, but that's just one instance. So what we want to do is repeat this many times and see what kinds of values would be likely to occur just due to chance if we repeated this simulation or repeated this randomization process over and over. All right, so we're going to repeat this process many times, and then we're going to put this together into what's called a randomization distribution. So under the null hypothesis, we should expect the differences to be centered at 0, but just due to chance with randomization, we would get different values for the difference in mean. So let's see what we've got here in this diagram. We've got the original sample data, and this is from StatKey, and I'll demo this in a separate screencast, but let's just look at the results. Here's the data that was observed. Here's one of the re-randomization samples, the difference where the, the tea group was 0.7 higher than the coffee group just due to this re-randomization. Okay, and so we get this sampling distribution, which we'll call a randomization distribution. It's centered at 0. And then we're going to look at this and see how extreme our value of 17.12 would be. It's out here somewhere. We want to try to quantify that. And see then, is the null hypothesis a possible explanation or a plausible explanation? Could this be observed just due to chance? All right, well, it certainly looks like it could, but how likely would it be? And why do I say it could? Because there are values that are quite extreme, including as or more extreme than the observed value that we got. Now, you shouldn't be able to answer this question just yet, whether it's plausible, but we should be thinking about this, and we are going to get to this idea. But first, we're just going to think about measuring how likely or what's the chance of getting a value as extreme as this 17.12 if the null were true. So what we just looked at was not a sampling distribution the way we did in the beginning of 3, but this is specific to a hypothesis test. So a randomization distribution is a collection of statistics from samples simulated under the assumption that the null hypothesis is true. We'll see different ways that we can do this for proportion and for means, even for correlation and regression as we go on. But this is our first look at a randomization distribution. It shows what types of statistics would be observed just by random chance if the null hypothesis were true. All right, let's take a look at another example. I said we could do this for means or proportions. Let's look at a case with proportions. So another study looking at the relationship between drinking green tea and prostate cancer. So this was a study conducted on 60 men with PIN lesions, some of which turn into prostate cancer, so to investigate whether green tea helps prevent prostate cancer. All right, so in this study, half of these men were randomized to take 600 milligrams of green tea extract daily, while the other half were given a placebo pill. So there was a treatment and control here with a placebo. It was double-blind. Neither the participants nor the doctors knew who was actually receiving the green tea. So this is a randomized experiment. Now, this will be an appropriate technique to use for observational studies as well. We'd have to kind of rethink how we're visualizing or thinking about the randomization occurring. But for now, we'll focus on the experimental setup. Now, after 1 year, let's see, we had 60, so 30 in each group. Out of the 30 getting green tea, only 1 had gotten cancer. Whereas in the placebo group, 9 out of 30 had gotten cancer. So that might seem like a big difference. The question is, could this be explained just due to chance? So here are our hypotheses. Proportion of green tea consumers to get prostate cancer is P1. P2 is proportion to get prostate cancer among the placebo. All right, and then we're going to think about doing this randomization test again. We're going to state the hypotheses, collect the data, calculate the statistic. This is from the actual data, and we want to see if this difference of minus 0.267, that is a much lower incidence of prostate cancer in the green tea group than in the placebo group, is that likely to be explained by chance? So to simulate the statistics that could be observed just by random chance, if the null hypothesis were true, we're going to create a randomization distribution. Now let's take a look. Let's see. So how extreme is the observed statistic? Is the null hypothesis a plausible explanation? So that's our focus. I'm not going to get into the details of how to construct this. But suffice it to say, we could have a set of 60 tickets, 10 could have cancer written on them, 50 no cancer, and then you could shuffle them up and randomly assign 30 to one group and 30 to the other, calculate the difference in the test statistics each time through, and that would be the basis for carrying out a test. All right, so let's take a look. Here's the randomization distribution that's constructed under the assumption that the null is true, so it's going to be centered at 0. We'll focus on that, but let's see what we have. These are differences, p hat 1 minus p hat 2, between the proportions getting cancer in each group. Here's the observed data, right? 1 out of 30 in the green tea group and 9 out of 30 in the placebo. The observed difference. So much lower rate for group 1. And here's a randomization sample, 1 out of 1,000 of these that were generated by randomly kind of shuffling the data and seeing what could have occurred if this is all just due to chance, that you have 10 out of 60 that are going to get cancer, and the green tea has no effect at all. So let's find where is the observed statistic, and we're going to come back to that point, but it looks like it's pretty extreme, right? How extreme is it? It's way out here. So it would seem to suggest that perhaps the null hypothesis is not so plausible. We want to formalize that idea, but let's just note one thing here at this point. A randomization distribution simulates a null hypothesis, so we should always check that the randomization distribution is centered at the value of the parameter given in the null hypothesis. So here our null hypothesis was p1 equals p2, but in another sense it's p1 minus p2 equals 0. So that's why this is centered at 0. That will be different than from the bootstrap, right? The bootstrap is centered at the statistic, plus or minus twice the standard error, but the distribution is centered at, in this case it would be centered at p hat 1 minus p hat 2 rather than p1 minus p2. Rather than 0, right, the hypothesized value. Okay, so we'll come back to that once we've kind of gotten through the randomization approach a little bit further. All right, so here's the basic setup we were just looking at, and this is centered at 0 because of what I was saying. The null hypothesis p1 equals p2 means our null value for the difference is assumed to be 0. All right, so let's go back though to the other example, because one thing that you should notice here is that this is very extreme. There should be no doubt that this is too extreme to be explained just by chance, right? It didn't even really happen maybe once or twice out of 1,000. Over here, the tea versus coffee, remember we had an observed difference of, let's see, it was about 17.12, wasn't it? There it is, 17.12. Tea and coffee. And here's our overall randomization distribution. What we want to do, what do we do when the extremity of the observed statistic isn't obvious? Well, we need a formal way of measuring how extreme a statistic would be if the null hypothesis were true. And that's what we're getting to, the idea of the p-value, which is one of the challenging ideas in inferential statistics, but I want you to do your best to get a clear grasp of this. The p-value is the proportion of samples when the null hypothesis is true that would give a statistic as extreme or more extreme than the observed sample, right? So in this case, the observed 17.12. Now, how we define extreme or more extreme is something that we're going to take a close look at as we go. All right, so here is our randomization distribution. We've identified where the observed statistic is. Now, using the stat key tool, we'll see that we can click on right tail to find out how extreme it is in this direction. And the way we're going to measure how extreme it is again the proportion that are as extreme or more extreme than the observed sample. We want to know how far out in the tail it is. So in our simulation of 1,000 of these, only about 2.6%, 0.026 of the time did we get a result this extreme or more. Well, that seems pretty unlikely, but that's our measure now. That's going to be our p-value. So this is the distribution of the statistic if the null were true. Here's our observed statistic, and here's our p-value. Okay? The proportion as extreme as the observed statistic or more extreme, because we want to know how likely this could happen. Okay? If there is no difference between tea and coffee, we'd only see this results this extreme 26 out of 1,000 times. That's how we get the 0.026. If we could count the dots, we'd count 26 of them out at or beyond this point in the tail. All right, so calculating a p-value, first we need to generate the randomization distribution by thinking what kinds of statistics do we get just due to chance if the null were true, and then we need to think about how to calculate what it means to be as extreme as our original sample. Now, last time we saw both one-sided and two-sided alternative hypotheses. The same thing's going to hold here, so we'll have to think in each case how to calculate what it means to be as or more extreme. Now, for the green tea supplements data, we were thinking our alternative or research hypothesis was that the rate would be lower in the T group than in the control group. So we're looking for a value in the left-hand tail as or more extreme and the negative 0.267. So this is a slightly different drawing, but it shows that the left tail probability, and StatKey calculates it for us, is just 1 out of the 2,000 really. So we get 0.0005, so much less even than 1% of the time. So it seems extremely unlikely. So this is the distribution, assuming the difference is 0. Here's our observed statistic. Here's the p-value, the proportion at or to the left of the alternative. Okay, so 1 out of 2,000 times. Pause the video and think about this question. This is for the correlation coefficient. Use the randomization distribution shown here to test rho equals 0 excuse me, versus the alternative rho, the population correlation greater than 0. So I want you to match the sample statistics R with the p-value, given the logic that we've been talking about. Which sample statistic goes with which p-value? Okay, so give that a try, and I'll come back to you. Okay, so let's take a look. Here, the 0.1, well, let's start with the most extreme, the 0.5, right? That's way out here somewhere, so it's very unlikely to get values at or beyond that. So that is going to be our most extreme value. So that one goes with 0.5. R of 0.3 is not quite as extreme. It's in here. So 0.3. The probability to the left is certainly more than 0.015, but not as much as at 0.1. So the 0.015 will go with R of 0.3, and R of 0.1 is the least extreme, the least inconsistent with the null. So that gets a p-value of 0.035. So this is the area to the right is about that 0.035. Okay? So I hope that makes sense for you. But that's the logic that we're trying to get to here. All right, so let's continue and summarize a little bit. For alternative hypothesis, here we had the right-hand tail, so we're looking at the probability at or beyond in the right side. Green tea in the left side, so we're looking at the left-hand tail probability. Upper tail versus lower tail. Okay. Now, what about a two-sided alternative? Well, we're getting to that. So one-sided, we have either a greater or less than, but a two-sided contains has a not equal to. So how would we think about extreme in a case like that? So the p-value is the proportion in the direction specified by the alternative. So the way we're going to do that in a two-sided alternative is to look at the smallest tail. So to try to think about how extreme it is, and then double that to take account of the fact that it could have been extreme in the positive direction or in the negative direction. So we'll think about that by revisiting the tea versus coffee. And let's say that we're just wondering which one is better. We're not sure. So our alternative hypothesis is just that one might be better than the other. So the null is they're equal. The alternative is they're different. So here's the setup now for the same randomization. Here's our test statistic of 17.12, but the way we're going to calculate the p-value now is to double this tail probability. So why did I click right tail here? Well, because this area to the right is much less than the area to the left, right? We're taking the smallest tail, so the p-value is twice the proportion in the smallest tail, in this case to the right of the original sample statistic. If we had had, say, a negative 20 as our test statistic instead of 17.12, if we observe this, then we'd click on left tail, we'd get the probability to the left, but once again double it, recognizing that our alternative is not equal rather than just one-sided. So if we're naive and we don't know what is the difference, then the chance of getting a value extreme could be in either tail. So that's kind of the logic of doubling it. I know the logic of this doubling is a bit tricky, so try to wrap your head around this and take a look in the reading as well to try to internalize that. So just to summarize, here's an example where the observed statistic is 2. If it's positive 2, the null is 0, the alternative is greater than 0, so different setting just for one sample case. Here's 2. We're wondering if we can reject this null hypothesis or if we have evidence against it, so we want to calculate the p-value. Right tail in this case, left tail when we have negative 1 because we're on that side. If it's a two-sided alternative, and then if we were over here, we take the value to the right, and then we double it. Okay, so we get 0.088. Now in this case, let's say with the negative 1, what if our alternative had been greater than 0 and we just got a value that went totally in the wrong direction? Well, then the correct p-value would actually be the area to the right here. Okay, it's not something that comes up a lot, but usually when you see results going in the direction opposite to what you even expect, it's common to just say, well, the p-value is greater than 0.5, and what we saw is not unusual at all. So we'll come back to that point. One thing when you're comparing two groups, make sure to note the order of the groups, because the p-value, the way you calculate it, is going to depend on what you're calling p1 and what you're calling p2. So it can be calculated based on the direction of the alternative hypotheses as long as the order in the alternative matches the order when the statistic is calculated. So the x bar 1 minus x bar 2 should match the mu 1 minus mu 2. If you got them turned around, then the two would be disagreeing with each other. So just as a check, and then you can also do like what we did at the beginning, look at the box plot and make sure that the conclusion matches what you're getting with the p-value. Right, with the box plot, it suggested a difference between the two groups, and so we weren't surprised that the p-value should be small. So as a check, remember that if the data support the alternative, the p-value should not be more than 0.5, right? We're looking out in the tail. Okay, so to summarize the main ideas here, and there's a lot to digest here, so make sure that you tune in to the examples and activity. Screencast. So the randomization distribution shows what types of statistics would be observed, what kinds of values, just by random chance if the null were true. A p-value is the chance of getting a statistic as extreme or more extreme than that observed if the null is true. A p-value can be calculated as a proportion of statistics in the randomization distribution as or more extreme than the observed sample statistic, and how we define or think about that depends whether it's a one or two-sided alternative. All right, so that'll end this lesson, which is just to go through and introduce and teach the main topics of section 4.2. And separately, I'll post the example and activity screencast, so make sure to check those out. All right, thanks for listening and take care.